All right. If you got a number larger than 0, raise your hand. Larger than 0? Good. All right. Larger than 1, raise your hand. Good. What is it? 0.5. Yeah, 0.5. So we have a net force. We have a net force of 500 newtons that way. We have a mass of 1,000 kilograms, and we're solving for A. Ordinarily, 500 divided by 1,000 is 0.5?
Yes, sir.
Sure. All right. Questions?
So how fast was he going?
We don't know yet. Well, all we know is he has an acceleration of 0.5. He might be traveling at 100 meters per second, but we only know he has an acceleration of 0.5. We don't know how fast he's going. We just know his acceleration. Other questions? It's not a lot. Yeah, it's not a lot. Okay. Terminal velocity.
Oh, air resistance.
Air resistance. Now we're talking about air resistance. Okay, so here's you. It's your 18th birthday. You finally get to be a skydiver, and you're like, for my 18th birthday, Mom, I want to go kill myself. I mean, go up in an airplane and jump out of an airplane. And she says, all right, you're 18. You can make important decisions about your lethality. So you get in an airplane, you get your parachute on, and you jump out of the plane. At that moment you jump out of the plane, what is your acceleration? Negative 10 meters per second. Because there is no air resistance on you, you're going to start falling at negative 10 meters per second squared. Okay? And you're going to get faster. A second later, you're going to be at 10. A second later, you're going to be at 20. A second later, you're going to be 30, and so on. So terminal velocity applies when there is so much air resistance that there is an upward friction force that cancels out your downward weight. So you jump out of the plane, and immediately you have a downward weight equal to mg. And you just set your downward weight into equal to ma, and now you have your acceleration. Set them equal to each other, and when you do, when force net equals w, and the m's cancel out, a equals g. Do I need to do that, or can you do that in your head? Please do that. Okay. So when you set your weight equal to your net force, I can't believe I did it again. I have got to, every time I write W, meaning weight, just say, Mr. Byers, you're doing it wrong. FG. Yeah. You did it again, Mr. Byers. Stop doing that. This is the way you were taught, but you're not supposed to teach us that way. Okay, so FG equals F net. Okay. So the mg equals the ma, and your m's cancel out, so your acceleration is equal to g at the moment you jump. Make sense?
Yeah.
Now, woo, you start falling, and as you fall, your air resistance increases. By the way, air resistance is a product of your profile, how fat you are, whatever the Earth sees. So this is my profile, my aerodynamic profile. If I turn 90 degrees, that's my aerodynamic profile. So if you want to go really fast, roll yourself into a ball or make yourself a spear. You're going to like aim at somebody, when somebody else is falling, I'm going to get him, and you make a spear right for him. Like in movies. They do that all the time in movies. Like, I'm going to get him, and they bam, and they hit people. Yeah, I don't know if that's possible. You'll have to talk to somebody who actually jumps out of a plane for a living. It seems like that would be extremely hard to do, to like aim at somebody who's falling and you're falling too. But anyway, drag, fluid friction, applies an upward force, and eventually you get to a terminal velocity. A terminal velocity means your net force is 0. When your net force is 0, so your F net is equal to your gravity weight minus your friction. when your gravity weight is the same as your friction, your F net becomes 0. And when your F net becomes 0, what does your acceleration become? 0. Okay? Even when you cancel out the m's, still 0. So you can sum all these equations up to say that acceleration is your F net over your mass. And your F net is your weight minus your friction force over your mass. So when your weight and your friction force are equal, the numerator of that fraction is 0, so your acceleration is also 0. That's wonderful. Don't feed the ants.
I think it would be possible to hit someone. I think like
Possible, absolutely. Possible, but like wicked hard. Just because of the changes in acceleration, and it'd be really hard to do.
it's like a, you know, like you're like
Okay.
going across the water, or like say you're laying on a skateboard, you're riding down the hill, you like put a hand down and you start turning. It's like slight adjustments in the air.
But there's nothing slight about your air resistance. So your profile like this and like this is dramatically different, and it actually your velocity is going to be much different. But moving on. Okay, maybe that's something we can see if the internet will answer. All right, now when weight is larger than drag, or sorry, when weight down is equal to drag up, the forces are in balance, the net force is 0, no acceleration, constant velocity. We call this equilibrium. We call this equilibrium when you have no net force. Now on the next slide, he's going to pull his chute. And I'd like you to, while I take 10 seconds to press the button, what I'd like you to do is talk with your neighbor what happens specifically when he pulls his chute. So do that right now. I'm going to press the button in about 10 seconds. Okay, so he pulls his chute. And what happens to the drag? It gets really big. And suddenly he moves up, right?
Does he actually move up?
No. No, that's what you see in Hollywood, though. When people pull their chute, suddenly the guy goes, phew, because the cameraman's still going down. The guy is not going up all of a sudden. He's just going down slower. Yeah. He now has an upward acceleration, but his velocity is still down. And we learned in kinematics that when you have a velocity and acceleration that are of opposite signs, what's your motion doing? Slowing down. Okay? When your velocity and your acceleration are the same sign, you're speeding up. When your velocity and acceleration are opposite signs, you're slowing down. So he pulls a chute, poof, and now he's slowing down. The cameraman's still going down, so it looks like he's going up, but he's not going up, he's just slowing down. And why is he slowing down? Because now, all of a sudden, this fraction becomes Fg minus Ff over m. Now we have a really big force of friction. And that force of friction creates a net force that is in the upward direction, the direction of friction. Okay. So you pull the chute, whoosh, and now we have a whole bunch of friction in the upward direction. Has the weight changed? No. I mean, he was always attached to the parachute the whole time. His weight hasn't changed, so his upward friction force is large, his downward weight is exactly the same. Now we have a net force in the upper direction, in the direction of friction, and that leads to an acceleration in the upper direction.
Acceleration towards 0.
Well, what happens then? If your dynamic fluid friction, air resistance, is based upon velocity, what is happening when there's an upward acceleration? What is happening to his velocity? Slowing down, slowing down, slowing down. And eventually, as he slows down, this is what happens. This is a great animation. As he slows down, his velocity, so he hasn't pulled the chute, he pulls the chute, big, huge friction, but now as he slows down, his friction gets smaller and smaller and smaller and smaller, till once again, eventually his friction is the same as his weight. So that means he's going the same speed as before, right?
Yeah.
No. No, because his friction is less because his velocity is less. His friction is less because his velocity is less. So you have two terminal velocities. What? How can that be? I know. You have two terminal velocities. You have terminal velocity without your parachute, which is fast, has very little drag, and you have terminal velocity with your parachute, which is slow with lots of drag. And if you packed your parachute properly, your terminal velocity shouldn't be more than about 20 miles per hour. Otherwise, you're going to break your legs. We aim for like 5 miles an hour. Yeah.
Is air resistance like a constant thing, or is it dependent on weight?
It depends on aerodynamic cross-section, that's the profile, your texture, and most importantly for our discussion, your velocity. So the faster you are, the more air resistance you have.
What altitude do you use?
Yeah, the density of the air would play a very small role. But the density of air is pretty small. The density changes are very, very small from like 15,000 feet to where you are. If you're jumping at like low Earth orbit like crazy people, then it would change, but it wouldn't change much for us. Hey, look, it's a giraffe.
I think you said a giraffe. I was looking for a giraffe.
Oh, look, a giraffe. Okay, we can call it a giraffe. So this is a giraffe of velocity versus time, and you also might notice it's upside down. So the velocity here is 0 through 60. It should be 0 through negative 60 because, you know, velocity down is negative. So you jump out. You're going fast, 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 fast. So you're slowing down. Why are you slowing down? Or why is not your actually? Why are you not slowing down? Why is your speeding up being less? Exactly. You're encountering air resistance reaching terminal velocity in there. Terminal velocity. So this is you cruising along with terminal velocity, enjoying your trip, and then your neighbor says, "Pull the chute." And you're like, "Okay." So you pull the chute, and now you go whoosh. What's happening here? You're slowing down because you got a lot of air resistance, and then once again you attain terminal velocity. I think this very graph is on your mid-unit mini quiz. Okay.
Just take a picture.
It's on the line, or you can take a picture of it.
It's on the line.
It's on the line. Yeah. It's on the line. It's in the Googles. It's on your tube. So you can view it on your tube.
What type of question could you ask? Like where it's like.
Yes. I would put letters all over I would put letters on the graph, and I would say, describe what's going on at point A. Describe what's going on at point B. What happens at point C? That's what I would ask. Okay. Are we ready to move on?
Wait, can I take a picture of this real quick?
I don't know. Can you? Do you want to use your phone? Yeah, hurry. Only because some people are scribbling for some reason.
Phone jail.
Yeah, phone jail. Put it in phone jail.
Thank you.
All right, cool. All right. Just to plant a seed, we'll pick this up again soon. I have a worksheet for you, which I want to pass out. What happens when you have a block on an inclined plane? So we'll pick this up again in the future, but I want you to think about, digest this, if you would.